I started off as an experimental psychologist. And the good thing about that was that we beat the hell out of evidence over and over and over again. So I'm very conscientious about evidence, and when people talk in these airy-fairy ways, I will not mention names, there's always this thirst to what's actually happening in the real world, and how do we find out about it, and how do we test things in the real world. And that became possible with regard to consciousness, I think, at least in modern science. In the 1970s, when Helmholtz's hypothesis from the 1840s, I don't mean to wander from the point here, Helmholtz was a very great scientist. He was a great physicist, great physiologist, a great student of both hearing and vision. And at one point he proposed that the visual system must be making unconscious inferences about things that we see, which is obvious when you look at eye movements, for example. When you think you're reading a page, the fact is that you're not. You're mostly filling in. And whenever you fixate on a word or on a phrase, whatever, you're momentarily conscious of that, and then your eyeball rotates like a billiard ball, and it's ballistic, and then it jumps to another point, and you can take another fixation at that point. You take fixation, 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 little ones. They're all little ones, little patches, and your brain brings it together and makes it conscious. And Helmholtz was practically run out of town for proposing that, because this violated all the educated Western intuitions that we have, that what makes the difference between humans and other animals is rationality, logic, reasoned discourse, all those wonderful things, which are indeed wonderful things, and mere animals were different. So Aristotle had a hierarchy. If you were a philosopher, of course, you were on the top of the hierarchy. And that still persists today in philosophy, so that every philosopher I know, at least, seems to develop arguments that show that he is conscious, but not too many other people are. And this is sort of understandable, but it's not true. So there was this hierarchical notion which dominated Western thought for such a long time, until we ran into these awful things called computers. And by the 1970s, so Helmholtz's idea was roundly rejected and denounced. And so by the 1970s, what we had was a so-called machine metaphor for this wealth of unconscious processes that our brains are doing every single second, every single fraction of a second. So if we walk away from the cortex for a moment, there are two balls hanging underneath of the back of the cortex called the cerebellum, or the cerebellums, I suppose these days. And they're very, very important. They have either as many neurons or more neurons.
4 times as many.
Yeah. 4
Really?
times.
They have 4 times as many neurons.
Smaller, but more of them, yeah.
That's amazing.
That's the cortex.
But they're little neurons, and they're wired very differently from the cortex. And the repeated stories from medicine, and I believe animal operations as well, is that you can get rid of the cerebellum, or at least much of the cerebellum, and maintain a stream of consciousness. And you think that's correct? Is that
Yeah,
right?
it's like computer-wise, it's like a coprocessor. It's not essential for anything, but it's helpful for a lot of things.
So there's a great deal of unconscious processing going on in the brain and in the spinal cord and the peripheral neurons that pervade our bodies. That is not directly conscious, but I should say that a lot of it kicks off regions of cortex, which emerge in the conscious stream that you are experiencing right now. This is a beautiful illustration that Natalie and an artist worked on. And it's basically, you can think of it as foveation. I'm pinpointing my fovea at rather about this much. If I extend my arm like this and put up two fingers, that's about the size of a foveal fixation. And we weave them together, or rather our brains weave them together for us. And what becomes conscious, of course, is not the little foveal fixation, but rather this enormous scene, which is actually much larger than the real visual field if you measure it carefully. So we fill in all kinds of really important stuff. And so we have a three-dimensional environment. We have lots of people sitting here. We're trying to communicate with each other, all that stuff. And it comes from little fragments of input. And the brain is just very smart to make sense of all that. And this goes to Mark's point that verbiage is not necessarily either the highest or the only way to think about these things, because sensory motor interaction, and it always is sensory and motor, even speech, for example. So this is psycho, and the sensory part of the brain, the posterior half of the brain, is the most vivid source of conscious vision and olfaction and taste and hearing and so on. If we think about all those lines that are going into cortex as being bidirectional, and bidirectional irritates all the engineers I know, because engineers know perfectly well that when you put a microphone next to a loudspeaker, that the circuit's going to blow up for obvious reasons, right? It goes into this howling siren sound. And basically, one of the tricks of electrical engineering is to avoid feedback loops like that. Now, the weird thing about the cortex is that it's simply filled with feedback loops like that, and yet it survives. Now, it doesn't always survive, by the way, because when you have an epileptic fit, what you're getting is this exactly out-of-control feedback loop. So it doesn't always do that, but children sometimes have temporary epilepsy that they grow out of. And in that process, there's some kind of balancing happening against catastrophic events. So this is a system that is ready to crash at any moment, and the reason why it makes sense that it is ready to collapse at any moment is because it must respond to totally unexpected inputs at various times. And it has to respond within about 100 milliseconds if you're an average mouse. So cat starts chasing mouse, mouse starts zigzagging, and the decision time for that process is about 100 milliseconds, maybe 200, whatever, very fast. And your neurons are relatively slow. They're much slower than the switches in a computer. So there's this weird organ called the cortex. And we know, in fact, I believe, in my mind at least, it was a neurosurgeon at the Montreal Neurological Institute who discovered around 1934, it was published in 1934, that cortex is the organ of mind. And by mind, Penfield certainly included consciousness, although mind also has some unconscious aspects. But that he found that essentially by studying what turned out to be 1,200 seriously epileptic patients who were not curable by less invasive procedures, and essentially had conversations with the patients while the cortex was being stimulated. So the mind, the conscious mind, but also the unconscious part that we call mind, short-term memory is an example. The conscious mind is an aspect of this vast range of phenomena in the world that can be understood in various implementations, if you will, of biological principles.
I'll just tell you what you're seeing. Huge number of neurons, and he placed it on
So 80,000 or 100,000?
yeah, 100,000.
Yeah.
And I think he used his own head. He imaged his own head to get the connectivity and where the areas were and placed them in 3 dimensions on this and then ran it, which took a ton of time to run. And this animation represents probably like a month of simulation time. What came out were these beautiful waves that look very much like what a wave would look like if you were actually imaging a brain like that, except there's details there that are really underlying the structure, connectivity, and the dynamics of single neurons.
I haven't seen this particular one, but variations on that. People are very interested in the frequency of the waves in terms of as a way for kind of the brain to test its predicted model against sensor input, and that this frequency is sort of unique to consciousness. And
How does this relate to the 20 years that you studied identical twins in the National
Yeah,
Institute for Mental
yeah.
Health and their development over time?
it hasn't been looked at, formally, as I know, but that is a good example as well of twins are themselves. They still have the same subjectivity, even though the same DNA and it's very similar environments. And whether sort of twins feel less, of that subjective sense of I, in terms of like, do they feel sort of a little bit more connected to their twin on these levels? But I think that this is also a window into the future in terms of being able to capture and quantify brain activity at these levels. Makes it a very exciting time for this kind of research. I think the technologies, the AI, if that's, I know that term is not loved by everybody, but I think a lot of things are converging right now. Being able to do the deep math, being able to do the modeling, to do the imaging, that it really feels like we're poised to really take a leap forward instead of a baby step forward.
I love that. And Bernie, is this perhaps a model to express a global workspace theory, global workspace dynamics?
Right. It's a little bit of a long story, so
We don't have a
maybe
long
we're
time,
not
so maybe we
having
maybe
at that possibility.
Yeah.
All you need to do is read the 800 pages of, and
So get you to about 2013,
Yeah,
and then you got to come back.
So an important aspect of this is the heuristic value. When I say heuristic value, what I mean is the idea that this model is testing the plausibility. This kind of model tests the plausibility of biological principles or the biological meanderings of actual neurons. So when Eugene was doing this, he wasn't spitting this out of whole cloth. He was inspired by what we knew about the activity and function of neurons, and he used that as the basis for essentially what you're seeing here. And what's really encouraging about this, as Jeff pointed out, is you see these propagating waveforms that look very much like what we're beginning to see with ever-improving imaging techniques in real brains. That's encouraging because that suggests that we may actually be on the right track, and maybe biologically based models can kind of be the harbinger of designing or implementing brains in artificial devices that may at some point instantiate conscious processing.
I mean, and as beautiful and technologically marvelous as it is, so the Euro standard is 84,600 sort of pixels or voxels that are measured. So each of the smallest things you can see is still 5 million neurons.
Exactly.
Right? So as good as this is, like we've got a way. We're still a plane flying over the city. Sort of looking. We're not at the dining room table.
That's right. Again, to borrow Mr. Spock's phrase from my favorite Star Trek episode, it's stone knives and bearskins. We're at the stone knives and bearskins stage, but someday we won't be.